So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to another computer science lecture. Today we are going to discuss chapter number 10 or section number 10 of new syllabus, Boolean logic. Whereas if you're following the old syllabus, then this is supposed to be chapter number 3, logic gates or logic building. So before we start, this chapter consists of logic gates. And what are logic gates? What is logic? Basically, logic means a reason, a condition or a criteria, whereas a gate is a path or an entrance. So logic gates are electronic components which only allow a certain input, or which only gives an output under some certain conditions, under some certain criterias, or the output they give are based upon certain conditions which are set priorly. So in our syllabus we have 6 logic gates, and the first one is an AND gate. When we are writing logic expressions, then we use the dot or a full stop to denote AND gate, whereas if we have to draw a logic circuit, then we draw it like this. This looks a little like an ice cream stick with 2 sticks in it, and this one is the output. We write AND gate like this. The number of inputs like this, we have to write A and B, so we write it like this, A dot B. The rule for AND gate is that output is one only if all the inputs are 1. Now this here is known as a truth table, and for every gate you should know how to make the truth table. If both inputs are 0, output is 0. If one input is 0 and the other one is 1, still it is 0. Why? Because the dot or the AND gate works just like multiplication. 0 multiplied by 1 is 0, or you go with 1 multiplied by 0, again it is 0. But 1 multiplied by 1, that is 1. So in AND gate, no matter how many inputs you have, you only get an output as 1, and unless and until all the inputs are 1. Now before we start further, the main question is, how do you make a truth table? So in order to make a truth table, first count the number of inputs. Like for example, over here we have two inputs, A and B, but in question when you have some logic circuits, you might have up to 3 inputs. In your Cambridge paper, when you get a question, you may have 3 inputs. So use the formula 2 raised to power n to determine how many rows your table will have, where n is the number of inputs. For example, if you have over here you have A and B 2 inputs, so 2 raised to power is 4, and as you can see the table has 4 rows, 1 2 3 and 4. And if we would have 3 inputs, then the table would look something like this: 1 2 3 4 5 6 7 8, because 2 raised to power 3 is 8. Now how do you fill the inputs? The rightmost input will have a value as 0 1 0 1 0 1 0 1, like this. This is the rightmost input column, and it has a value of 0 1 0 1 0 1 and 0 1, whereas the next one after it should have 2 zeros 2 ones, 2 zeros 2 ones, and the third one is supposed to have 4 zeros and 4 ones. In Cambridge we never have a truth table that has more than 3 inputs, but if you are, let's suppose at university level, sometimes you have logic circuits with 4 or more inputs. So 2 raised to power 4 is 16. So if you are making a truth table with 16 rows, then the rule is same. The rightmost column means A, B, C, D. D column would have 0 1 0 1 0 1 0 1 0 1. The B one would have 2 zeros 2 1 2 zeros 2 1. Then next one would have 4 zeros 4 ones, and the next one over here would have 8 zeros and 8 ones, and so on. But thankfully in Cambridge we never have a truth table that is bigger than this. And in Cambridge as well, the examiner usually fills the input part for you. In exam, when you are given a truth table to complete, you have this part already filled. You just have to work with the gates that are given in the circuits, and you have to fill out the output. That's it. Hope you have understood the truth table. Now we are going to move on. The second gate which we have is OR gate, and the symbol for that is plus. This is the symbol or sign for OR gate, and if you have to write it mathematically, then it is plus. Rule: output is 1 if any or all the inputs are 1. So these are the inputs. 0 plus 0 is 0. Like over here it shows that OR gate basically represents addition. Now 0 plus 1 is 1, and so is 1 plus 0. And when we have 1 plus 1 in maths, we would get 2, but this is in binary, so we cannot have a 2. 1 plus 1 over here gives the output as 1, because in binary language we only have 2 characters or 2 alphabets, a 0 and a 1, so we cannot have a 2 over here. The third one is a NOT gate, and it is depicted by this symbol, a bar. This is the symbol for a NOT gate, a triangle with a circle. NOT gate is the only gate which only has one input and one output, whereas all the other gates have at least 2 inputs. In Cambridge we always have only 2 inputs, whereas practically or in other curriculums we can have 2 or more inputs. Rule: output is the opposite of input. Since there is only one input, so 2 raised to power 1 would give you 2, and we have 2 rows. The first one is a 0 and the other one is a 1. Now whatever is the input, the output is always the reverse of it. Like if a 0 goes into this gate, you get a 1, and if a 1 goes over here, you get a 0. Next we have a NAND gate. A NAND gate is basically a combination of AND gate and NOT gate. So NAND is basically short for not AND gate, and it is written like this: A plus B, that is A and B, and there is a bar on top of it to denote that the answer has been reversed. Rule: opposite of AND gate, output is 1 if any or all of the inputs are 0, because this 0 multiplied by 0 should give you 0, but since there is a not involved denoted by this circle, since the output is reversed, so we get a 1. 0 multiplied by 1 should give you 0, but because of this bar, this reversal, we get a 1. Again 1 multiplied by 0 should be 0, but we get a 1. 1 multiplied by 1 should give you 1, but because of the not part, we get a 0. The next one is NOR gate, our fifth gate, and the symbol is A plus B and a bar on top of the whole bracket. It is the opposite of OR gate or the NOT OR gate. Output is 1 if none of the inputs are 1. 0 plus 0 should give you 0, but since there is a NOT involved, so the output is reversed and you get a 1. 0 plus 1 should give you 1, but again output is reversed as 0. 1 plus 0 should give you 1, but you get a 0. 1 plus 1 should be 1, but it gives out a 0. Next we have a XOR gate or the exclusive OR gate. The symbol is like this and mathematical notation is like this, a plus with a circle around it. The rule for it is that output is 1 if any one but not all the inputs are 1 or 0. Means if all inputs are different or not same, then you get a 1. Otherwise, if all inputs are same, either they are 0 or either they are all 1, then you get a 0. 0 or XOR 0 is 0, 0 1 is 1, 1 0 is 1, but 1 1 would give you a 0. So these are our 6 basic logic gates, and you need to learn these rules by heart, and you also need to learn how to make the truth table, this part. Now another thing which we have in this chapter is that you can use a NAND gate in order to represent each of the primary gates, the NOT gate, the OR gate and the AND gate. And why do we do so? Because each gate is, all the 6 gates, when they are used in electronic circuits, so there are different components which represent different gates. Sometimes a company might not have the components required for OR gate or AND gate, but they might have an excess amount of components for NAND gate, so they can use the NAND gate to create any other gate. Or sometimes it might happen that because of cost, might be possible the cost for NOT gate components or OR gate components is very high, whereas the cost for NAND gate component is not that much high, so we would use the cheaper components and join them in such a way that it would work as the higher price components. NAND gates can be used to form circuit representing all other gates. Using NAND gate only, draw a circuit to represent OR gate. This is the circuit for AND gate. If you add 2 NAND gates in this sequence, it would become a NAND gate. It would become an AND gate. The first NAND gate has 2 inputs and the output is shorted as 2 inputs, and the answer you get would be the same, or the truth table you would get would be the same as an AND gate. If you don't believe me, you can draw a truth table over here and solve it out, or I'll just do it for you. I'll just copy a truth table and edit it. Okay, I don't have a short truth table. Let me just draw one. As we have two inputs, so we know that our table should have 4 rows, as 2 raised to power 2 is 4. And we are going to have one row for this would be A, this would be B, this would be A dot B, this part, and on top of that we would apply a bar in order to know that this is actually NAND gate and not AND gate. There you go. This is NAND gate, and then we have a second NAND gate. Let's call it the output as Q. And now you know the drill, that the last input would get a 0 1 0 1 in the table, and then after that we have 2 zeros and 2 ones. So 0 multiplied by 0 should be 0, but because of NAND we get a 1. Again same, and 0. Now this input is fed into this NAND gate such that when you get a 1, then it basically splits and goes over here and over there as well. So 1.1 should give you 1, and because of NAND it would be reversed and you are going to get a 0. The same is over here, but when this 0 comes out of here, then the 1 0 goes over here, and the same signal is sent over here. So 0.0 should give you a 0, but because of NAND the output is reversed, so we get a 1. And if you hide this part, if you don't look at it, if I just delete it, see, the table which I have left is the exact same as an AND gate. 0 0 0 and 1. See, 0 0 0 and 1. Thus it is proven that you can make an AND gate using 2 NAND gates in this sequence. Now this is how you make an OR gate, and you are going to get output as 1 if any of the output inputs is 1. You can make a truth table and try it for yourself. And if you want to make a NOT gate using a NAND gate, simply short both inputs together or connect both inputs together, and you are going to get opposite of whatever is sent as input. Again, you can make a truth table and you can verify it. Now the type of question you get are something like, either you're given a logic circuit and you have to make a logic statement and a truth table from it. Either you're given a logic statement and you have to draw a circuit from it. So this is the first type of question where you're given a logic where you have to create a logic statement for the given circuit. So this is the logic circuit that is given. So how do you solve it? First of all, we'll see A is going into this NOT gate and A is also going into this OR gate. So the first thing is A is going into NOT gate, so A is not 1. Then we have an AND gate, so we write it as AND. Next, in this gate, what we have the output of this OR gate. And what is the input of this OR gate? A or B. So I write this in a bracket that A is 1 or B is 1, this part. Or, because we have another gate over here, or what is there? A is 1 or B is 1, this part again, because the output from this is going as input over here and as input as over here as well. This is something known as a logic statement. Now if I simplify it, then I can convert it into logic expression. How can I do that? This is one way, A naught and A or B, or A or B. This is one way, but the actual way is doing like this, using only mathematical symbols. A bar dot A plus B plus A plus B. This is a logic expression. Now the Cambridge examiner gives you marks if you write this part, or you write this part, or if you write this part. Normally if we have this question for 1 mark, then you can write any of it. Although I would say, according to mark scheme, writing this is always better and guarantees you that you would get the 1 or 2 marks. But if you have a 3 mark question, like the examiner has asked, write down the logic statement from the circuit, and the examiner has given you 3 or 4 lines and is given that question 3 marks, then make sure that you write all of it. First write a logic statement, then simplify it, and then convert it into logic expression, in order to make sure that you acquire all 3 of those marks. If you just write any one of it, or if you just feel like, okay, I'm lazy, I am only going to write any one of these lines, then always write this one. Okay, now if you have to make, now usually the next part of the question, or mostly the next part of the question, says that draw a truth table from the given circuit, or from the logic statement which you have just created. So this is how you would make a truth table. First of all, if you have a NOT gate in the circuit, first of all find that. We have 2 inputs over here, so our table would consist of 2 rows, and it's always easy to find all the NOT gates. Now we have a NOT gate over at A, so first of all we find A bar, and it is the opposite of A, so 0 0 becomes 1 1, and 1 1 becomes 0 0. In the next step, after the NOT gate, we have A or B. Here we have found A plus B, and for my ease I have given it a name as C. Okay. Next I have A naught and the output from this OR gate, which I have just named as C. So this is C dot A bar or A bar dot C. You can write it in both ways. That means I would be considering this column, that is C, and this column, that is A bar only. I'll not be concerning with these 2 columns for solving this. The students sometimes do this mistake. They take this A and this C, and that gives you the wrong answer. So the best practice is to put your 2 fingers and track your work as you solve each line. Like put one of your index finger over here and the middle finger over here, and this would assure that you would not be stuck somewhere, or you would not be confused, or you would not be looking at any other column. So 1, this is dot, that means multiplication or AND gate. 1 and 0 gives you 0. 1 and 1 gives you 1, 0 1 gives you 0, 0 1 gives you 0. Now that we have found the output for this, I am naming it for the ease D. Now this D and the output from this C are combined here using an OR gate to find the final output of this circuit, that is Z or Z. So this is C plus D, and how do we solve it? This is C, this is D. Now we'll put our fingers on these two columns and solve it using the rule of OR gate. 0 plus 0 is 0, 1 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is also 1. Usually in these terms we have a part C that says which single gate can replace this logic circuit. So for writing the answer, what you would do, you are going to consider the 2 or 3 input columns and the output column, and you would see when they both were 0, you got a 0. When there was 1 in one of the inputs, you got a 1. Again, when there was a 1 as a single input, then you again got 1, and when they both were 1, you also got 1. Now that means that if there was any 1 in your inputs, you got an output as 1 as well. Now this is a rule for OR gate, that output is 1 if any or all the inputs are 1. See, this output matches with this one. That means you can write your answer as in the answer line, you can write OR gate because it satisfies the logic. I hope you have understood so far. If you have any questions, feel free to ask me. Please do share, comment, and subscribe to my channel. Take care. I'll see you guys in the next part of logic gates. Take care. Allah Hafiz.